So 1-2b, we're still talking about functions today. We're going to do some other properties of functions. We'll just call it properties of functions. Is that what we called yesterday's? I think so, yeah. All right, so we're going to have some functions, and we're going to find out where these functions are increasing or decreasing, what intervals. We're going to find their maximum and minimum points, okay, with our calculator. We're going to use our calculator for a lot of this stuff, so you might want to get that out. We're going to talk about symmetry and asymptotes, okay? So we've got 4 sections to do. Lots going on. So first we're going to talk about increasing and decreasing. And with these, you're always going to use x intervals. Okay. So as you read a graph from left to right, if your graph is decreasing, that means your y values are decreasing. And then if you're reading it from left to right as you go towards infinity and it rises, your y values are rising, that means it's increasing. There's a very formal definition in the book that I try to skip every year because it's terrible. All right, so let me show you a basic function that is increasing over its entire domain. That would be your basic cubic function, like y equals x cubed. If you were to graph y equals x cubed, you notice that as you read this graph from left to right, like if you were going to stand here, maybe you're on your skateboard or something, you would be climbing uphill the entire time. Okay? This graph is increasing on the x interval from negative infinity to infinity. The entire, all the x's, it's increasing. Something like exponential decay. Exponential decay. Do you remember, like, if you have a car and you drive it off the lot, it's not worth that much anymore, it's decreasing at an exponential rate. That would look like something like this. Okay? This one is decreasing on the entire interval, negative infinity to infinity. So this one decreases from negative infinity to infinity. Okay. Sometimes you can have a mixture of things. You can have something that looks like this. Let's go 1, 2, 3, 1. Let's say that we have a graph that goes like this, and it goes to a point right there. And then let's say it goes across here and then up. It's a really weird graph. Okay, it's probably a piecewise function. It has three kind of pieces to it. We're going to do some piecewise functions in this chapter. So this one right here, we can say that this graph is decreasing on this interval of x right here. Okay, it's going like this, and it's decreasing that entire time. So we would say this graph is decreasing from negative infinity to negative 3. You know, and the book likes to put a bracket there. I like to put a parenthesis. I'm not going to mark off either way, okay? And then this graph is constant. It's not increasing and it's not decreasing, okay? So it's constant from negative 3 to 0. Now, did you notice I'm always using x values here? Because people will mess this up. They'll think that this decreases to 1 because the y value is 1. That doesn't have anything to do with it, okay? The intervals that we're looking for where this function is decreasing or increasing or constant are the intervals of x. And then finally, I would say that this graph is increasing from what? Perfect. 0 to infinity. Yep, this entire interval here. So it's almost like you're looking at x like a number line, and we're saying, okay, this is what the graph is doing at these certain spots on that number line. All right, so let's do one. Number 1. Some of these are tricky. We'll do an easy one, then we'll do a super hard one. Number 1. F of x is equal to x plus 2 squared. And we are supposed to find the intervals where this graph is increasing, decreasing, or constant. Decreasing, constant. Okay, this one's not going to be constant, but. All right, let's graph it. You can go to your calculator. You can use your calculator on this stuff, which you're going to love. So we're going to go to our calculator, and we're going to graph parentheses x plus 2 squared. It's just going to be a parabola shifted 2 to the left. There we go. Okay, you don't have to draw the graph. You don't have to show work on any of these, which is really nice. You do it on your calculator, and you go, okay, this graph is decreasing on this interval right here. Decreasing all the way till I get down to that minimum value. So on my x right here, I'm decreasing from negative infinity to negative 2. And then my graph is increasing from negative 2 to infinity. Okay, and just like I said, if you want to put a bracket there around negative 2, you're more than welcome to. I always put parentheses. Doesn't matter to me. All right, so let's do kind of a weirder one, number 2. Let's do something like g of x equals the absolute value of x minus 1 plus the absolute value of x plus 3, and then minus 1 on the outside. I have no idea what this looks like. I'm super excited. I didn't do this one with them. I was rushing. I kind of did a different one that I didn't like. So, all right, so here we go. Do you remember where the absolute value is? You go over to math num, absolute value of x minus 1 plus math num, absolute value of x plus 3, and then minus 1. Ooh, that's different. That's fun. Is that fun, Jason? Yeah, okay. All right, so here we go. We're going to go and we're going to graph this, and it's decreasing until, what is that? Negative 3? Yeah, negative 3. Okay, and then it's constant here till we get to what, 1? And then it's increasing. That's a really fun graph. It really is. You guys are so lucky. Okay, so here we go. We're going to write it down. Intervals, x intervals, decreasing on this interval from negative infinity to negative 3. And then this one is constant, which is kind of different because we don't see a lot of constants a lot. Constant from negative 3 to 1. And then it increases from 1 to infinity. Fun, huh? You like those? Yeah, you should. Those aren't too bad. All right, that's the first part. Part B. It only took like 5 minutes, right? Oh, 8 minutes. All right, part B. We are now going to do some local and absolute extrema. Max and mins. Really fancy way to say max and mins. So a lot of times our graphs are going to peak and then go down in valleys and do all kinds of fun things like that, okay? It's where the graph changes from increasing to decreasing. So these points are very important. Now, we have some words that we need to know. So we have something called a local max, local maximum. I always just shorten it, local max. And then we also have something called a local min. Okay. We also have an absolute max and an absolute min. So let me go ahead and draw a picture for you, and I'll tell you here like which one's which. So let's suppose that I have a graph that looks like this. It's kind of a weird graph, huh? Kind of fun. And I'm going to plot some points on this, and I'm going to point out the important points, okay? So this point right here, I'm going to call point P, and this one I'll call Q, and this one I'll call R. Okay, those are the important points, because as you know, you can tell this graph, it's increasing. I should always draw that in green. It's increasing, and then it switches to decreasing. and then it switches back to increasing, and then it switches back to decreasing. Okay? So those are very important points. That's where the graph changes from increasing to decreasing. Now, a local maximum, excuse me, is going to be like the highest point in its neighborhood. Okay? So point P is a local max. Because as you reach this peak right here, you go back down, but it's not the highest one on our graph. Okay? Our absolute max is what? R. R is the absolute max, is the highest y value that our graph goes to. Okay? This one has no absolute min. Okay? There's none because the graph has arrows going down forever. So it'll go down to negative infinity. But Q is important. Q is a local min because in its neighborhood, it is the smallest point. Don't you like neighborhoods? Okay, so we'll just do one of these. We did these last year. Number 3, let's go ahead and graph this on our calculator and find any maximum or minimums. F of x equals x to the 4th minus 7x squared plus 6x. We're going to find the max and mins. We're not doing increasing or decreasing for this one. I mean, you could, but we're just going to find the max and mins. Okay, so go to your calculator. X to the 4th minus 7x squared plus 6x. Ooh, this one has an interesting stuff. Okay, first of all, it's off the graph. I can't see the whole graph, so I need to change my window. And I'm going to go to window, and I need a y that's a lot lower than that. So I'm going to try like y equals negative 30. And then I'm going to graph and see if that was enough. Oh, more than enough. Okay. So as you can see, this graph, there's a lot of maximum minimums going on. It dips down here, and then it goes up here, dips down here, and then it continues to rise. Okay? And so there are 3 important points, just like that graph I drew up there. We need to find this point, and that one. Those are our 3 important points. Now, do you remember how to find max min on your calculator? Do you remember where that was at? Okay, let's find this absolute minimum right here, the very lowest point, okay? So we're going to go second trace, which is calculate, and I'm going to find number 3, the minimum. Second trace number 3, hit enter. Now your calculator is going to ask you to go to the left side of that minimum. So I need to arrow that blinker, that guy, over there to anywhere on the left side of the minimum. And I hit enter. And what it did is it put a triangle in, saying, okay, this is where I want to get my estimate in. Now it's telling me to go to the right side of it. So I go over to the right, and now it has an area where it's going to find the minimum just there on my graph. Hit enter one more time, and there it is. You can round to 2 decimal places, so we have a minimum. You could even say absolute minimum if you wanted to. 2.06, negative 24.06. Okay. Some people will just list the y value as the minimum because that's the lowest it goes in the y. I like to just list it as a point. Okay, now let's go ahead and find that maximum. There's a local maximum right here, this point. So let's find that local max. Calculate number 4, the maximum. And now this time we're going to go to the same thing, the left side and the right side. Hit enter. So I have a local max at 0.46, 1.32. Okay. And then one more. Calculate the minimum again. Hit enter on the left, enter on the right, and then I have a local min at 1.6, negative 1.8, or 76, whatever you want to round to. Okay. Any questions on that? Do you remember doing that last year? We did. We did that on our calculators last year. Yeah?
Are we going to have to write, like, absolute minimum or less limit?
I'm not picky about that. I'm really not. Yeah. So, yeah, if you wanted to write local, max, it's fine. You don't need to. Just mins and maxes. I'm fine. All right. Moving on. That was part B. that only took another like 8 minutes. All right, part C, symmetry. There's all kinds of different symmetries and graphs and stuff. We're going to focus on 2 main symmetries because they're important. So if I have symmetry over the y-axis, then that means that my function is called an even function. It's an even function. We're going to have even functions and odd functions. So those are even functions over y equals, or over the y-axis. So let me give you a very basic y equals x squared, right? Y equals x squared is your basic parabola. Okay, not all parabolas are even functions though. If my parabola shifted left or right, it wouldn't be symmetric over the y-axis anymore. But this one, your basic y equals x squared, is an even function because it is symmetric over the y-axis. Now, another way that you can tell if something is an even function is if you pick a point on this side, like for example 3, 9, across the way, this will be the point, -3, 9. So with even functions, f of x will equal f of -x. They're going to equal the exact same thing because it's symmetric, right? That should make sense. If I plug in, say, a positive x over here, and I plug in the opposite of it, I'm going to get the same answer because it's even, because it's reflected over the y-axis. Now, the other one is not reflected over the x-axis. Reflected over the x-axis, those are usually bad because those are not functions. But if I am reflected over, here, let me put like, it's important. If I am going to reflect over the origin, origin is O, O is for odd functions. These are called odd functions. Okay? And then anything else would be neither. So even functions over the y-axis, odd functions over the origin. If you're symmetric or not symmetric over anything else, it's just a neither. So for these, a basic cubic function, not all cubic functions though are odd, but the very basic y equals x cubed. Okay, if you draw your graph like this, this is a cubic function, just y equals x cubed. And let's say we pick a point over here. Let's say that's the point 2, 8. 2 cubed is 8. And if I go over here across the origin, it's kind of weird, huh? Across the origin, and I get this point over here, this would be the point -2, -8. So for odd functions, f of x is equal to the opposite of f of -x. When I plug in 2, I get +8. If I plug in -2, I get the opposite, -8. So with even functions, you get the same number. With odd functions, you get exactly the opposite. Okay, and there's different ways to check for symmetry. Let's do one. Number, what are we on? 4. We're almost done. That was 18 minutes already. Number 4. Let's say that we have f of x equals 2 over x. Is this going to be even, odd, or neither? Most of them are neither, really. Most graphs are. So I can go ahead and graph this on my calculator. Let me zoom 6 it. All right, so here's my graph. Oh, that's pretty good. Definitely not symmetric over the y-axis, right? And what I like to do is I like to pick a point. Like I'll hit trace, and I'll pick x equals 2. If I pick x equals 2, I get 1. And then let's pick x equals the opposite, -2. Guess what I get? -1. So I plugged in opposites, and I got opposites. This is definitely a what? Odd function. It's odd. And you can tell, I mean, saying something symmetric over the origin is kind of weird, but it's symmetric across this way. All these points are symmetric across the origin. All right. right, last part. There is a light at the end of this tunnel, and I only have a few more minutes left. Letter D, asymptotes. We're going to spend a great deal talking about asymptotes in the next class, or the next chapter, but your calculator wants you to do these on, or your book wants you to do these on your calculator first, okay? So there are going to be two types of asymptotes that we're going to focus on, and those are going to be horizontal asymptotes. Horizontal asymptotes are going to be y equals a number, and then we're also going to have vertical asymptotes, which is going to be x equals some number. Okay. All right, so basically what's going to happen is you're going to have a graph, and it's going to maybe look something like that, okay, or something like that. So let's talk about what the asymptotes are here. The asymptotes are not going to be like lines on your graph. You can see them. Okay, they're actually things you can't see, so it's kind of tough to find out what an asymptote is. For this one, right through x equals 2, the graph, as you're going to, y is going to infinity or y is going to negative infinity, you get a vertical asymptote of x equals 2. Okay, that's how you find vertical asymptotes. You go to y as y goes to infinity or negative infinity. Now, the way that you find a horizontal is as x goes out to infinity or as x goes out to negative infinity, this graph is getting closer and closer and closer to y equals 1. Okay, so on your calculator, you just you trace it. You trace it out as far as you can. So let me show you an example. Number 5. All right. Let's do like a fun one. Let's do this one. F of x equals 2x squared over 4 minus x squared. Okay, and it's going to ask you to find any vertical asymptotes or any horizontal asymptotes. You don't have to draw the graph, okay? I'll probably draw it just so I can, mark it up and explain it to you. So go to your calculator. What you want to do is you want to do parentheses 2x squared divided by parentheses 4 minus x squared. Okay, and then we're going to graph. Now you can probably already tell just by looking at the equation that there's going to be a problem at 2 and negative 2. Did you see that? 2 and negative 2. There's some problems there. We talked about continuity, right? Yeah, so those are discontinuities, and they go to infinity. They're infinite discontinuities. So as you look at the graph, let me draw it real quick. It goes like this. There's some weird parabola guy in the middle. We're going to graph these by hand next chapter. Are you super excited? Yeah, same. And it looks like that, okay? All right, so we can tell that there's two asymptotes, two vertical asymptotes here. And those vertical asymptotes are actually pretty easy to tell because they're whatever x can't be in the bottom, usually, unless it's a hole. So this would be x equals plus or minus 2. There's two vertical asymptotes on this graph. Now the horizontal asymptote is a little bit harder to find. Okay, so what you want to do is you want to trace your graph, jump on your graph, or you can go to the table. I don't know which one you guys like better. But as I'm going out towards negative infinity, do you see what my y value is approaching? It's never going to approach negative 2.1. We're not going to do that to you. It looks like it's getting closer and closer to what? Negative 2, right? The y value. So then your horizontal asymptote, which is coming through here, is going to be y equals negative 2. If you don't like to trace it out, you can go to the table. Look at, you can go out towards negative infinity or positive infinity. It's going to be negative 2. Your graph, it's rounding, but it's going to be negative 2. So that's the horizontal asymptote. Okay. Woo, 24.